In two-dimensional geometry, we saw how to find the coordinates of a point that divides a line segment in a given ratio. In this module, we will explore how the coordinates of a point that divides a line segment in space are found. Let AB be a line segment in space. We have another point C on AB, which divides the line segment into two parts in the ratio m:n. We will find the coordinates of point C that divides line segment AB. Let the coordinates of point A be x1, y1, z1, and point B be x2, y2, z2. Let the coordinates of point C be x, y, z. We draw perpendiculars from points A, B, and C onto the xy plane. Let the feet of the perpendiculars from points A, C, and B on the xy plane be P, R, and Q, respectively. Lines AP, CR, and BQ are parallel to each other. The line joining points P, R, and Q lies on the xy plane. Now, we draw a line parallel to the line PQ and passing through point C. This line intersects line PA externally. Let the point of intersection be D. Let the point of intersection of this line with BQ be E. We can observe that quadrilaterals DPRC and CRQE are parallelograms, since lines AP, CR, and EQ are parallel to each other, and lines DC parallel to PR and CE parallel to RQ are also parallel to each other. Since AD and BE are parallel to each other, in triangles ADC and BEC we have. This implies that triangles ADC and BEC are similar. Therefore, this relation holds true for the triangles. From the figure, we can observe that the left-hand side of this relation is equal to m divided by n. On the right-hand side, we can observe that DA is equal to DP minus AP, and BE is equal to BQ minus EQ. Since DPRC and CRQE are parallelograms, we can observe that DP and EQ are both equal to CR. Substituting the values, we get the relation as shown. Therefore, the z-coordinate of point C that divides line segment AB in the ratio m:n is as shown. Similarly, using the same method, the other coordinates x and y of point C can be found. Therefore, the coordinates of the point that divides the line segment in the ratio m:n is as shown. Now, we will see some special cases of the section formula. Again, let's consider line segment AB in space. If point C divides AB exactly into two parts, then C is dividing AB in the ratio 1:1. Therefore, m:n is equal to 1:1. This implies that we can consider point C as the midpoint of AB. Substituting in the standard formula, we get this. Therefore, the midpoint of a line segment is as shown. If point C divides the line segment in the ratio 1:k, we get this. The coordinates of the point that divides a line segment in the ratio 1:k is as shown. We have seen how to locate a point in a two-dimensional plane with respect to its distance from the reference axis. In three-dimensional space, we identify a point with respect to the distances from the three reference planes. Let's see what these reference planes are and how to locate a point in space. We take two planes perpendicular to each other. The intersection of these two perpendicular planes is a straight line. Let's take another plane perpendicular to both the existing planes. With the intersection of this plane with the two existing planes, we get three lines mutually perpendicular to each other. These lines are called axes and are named as X, Y, and Z. The point of their concurrence is called the origin. The origin is denoted by the letter O. By convention, we consider the XY plane as the horizontal plane. Distances are measured starting from the origin. Distances measured in one direction are taken as positive and in the opposite side as negative. For example, the distance measured from the origin along the x-axis along the direction shown is taken as positive. The distance measured from the origin in the opposite side is considered negative. To indicate this, we assign the symbol x dash. A similar convention is followed for calculating the distances along the y and z axes. The plane formed by the x and y axis is called the xy plane. Similarly, the plane formed by the y and z axis is called the yz plane, and the plane formed by the z and x axis is called the zx plane. The xy plane, yz plane, and zx plane divide space into 8 octants. Here, XOYZ is an octant. This octant is enclosed by the XYZ axis. Similarly, the other octants are named according to the axis that enclose them. Any point in space is represented with the help of the distances that it measures with respect to the planes. These distances are called the coordinates of the point. Suppose we have a point P in space. The coordinates of this point are x, y, z. Each coordinate individually indicates the shortest distance of the point from the corresponding plane. For example, the coordinate x determines the shortest distance of the point from the yz plane. Similarly, the y-coordinate represents the distance of the point from the zx plane, and z represents the distance of the point from the xy plane. The coordinates of the origin are 0, 0, 0. The coordinate axes divide the coordinate space into 8 parts, called octants. The sign of the coordinates determine the position of a point in a particular octant. For example, the point 2, -3, 3 lies in the 4th octant. The x-coordinate of the point is 2. So we measure 2 units along the x-axis and mark a point. The y-coordinate is -3. So from this point, we measure 3 units on the xy plane in the direction of OY' parallel to the y-axis. We mark a point there. For the z-coordinate, that is 3, we measure 3 units from the point perpendicular to the xy plane. We can notice that the point lies in the 4th octant. The table shown here gives the details of the octant according to the signs of the coordinates of a given point. Distance between 2 points A and B in a 2-dimensional coordinate system is as shown. In this module, we will explore how to calculate the distance between 2 points in space. Let A and B be 2 points. Let the coordinates of A, B, x1, y1, z1 and B, x2, y2, z2. We need to find the distance between points A and B. Let's denote it with AB. Now, let us consider the planes passing through points A and B and parallel to the coordinate planes. We get a rectangular parallelepiped from the intersecting planes. We will take a point C on one vertex of the parallelepiped, as shown. Since points A and C lie on the same line parallel to the y-axis, point C will have the same x and z coordinates as point A. Hence, the coordinates of point C are x1, y2, z1. The triangle formed by points A, B and C is a right-angled triangle with right angle at C. Since ACB is a right-angled triangle, we get AB square is equal to AC square plus BC square. Next, we consider point D on the parallelepiped as shown. Since points B and D lie on the same line parallel to the z-axis, its x and y coordinates are the same as that of point B. Hence, the coordinates of point D are x2, y2, z1. Points D, B and C form a right-angled triangle with a right angle at D. Therefore, we get BC square is equal to DC square plus DB square. In triangles ACB and BDC, we have side CB as common. Therefore, we can combine the relations as shown. Next, we realize this relation with the coordinates. As we can observe, length AC is given by y2 minus y1. Similarly, length DC is given by x2 minus x1 and dB is given by z2 minus z1. Hence the distance between any 2 points is as shown. As a special case, the distance of a point from the origin can be found as shown.